Welcome everyone. This is a kind of novice Julia tutorial. So my plan today is hopefully we'll get everyone up and running with Julia, and you'll be able to follow along with this notebook I've put together. I'm going to leave this up for a couple more minutes as I introduce myself. So I'm Chase Coleman. I'm a PhD student at NYU Stern, and I'm studying economics. I'm also a member of an open source economics team called QuantEcon. And so the standard in economics is pretty bad right now in terms of software development. And so we're trying to teach other academic economists some new tools. So there's people that are as advanced as us or more advanced, but kind of the status quo isn't where we'd like it to be. So should I leave this up for a minute more? Are people still okay? So kind of in both. So I came across Julia partially because of both of these roles as PhD student and being a member of this organization, QuantEcon. In particular, there's another developer on QuantEcon who kind of pushed it on me. I was kind of Python and hell and high water. I wasn't going to learn anything else. But he kept pestering me, and eventually I said, okay, I'll try it for this one class. We were doing a Bayesian estimation class together, and there's some nice things about it. So hopefully, I'm not here to draw people away from Python and masses. I think there's room for both of them, and I frequently use both languages, but there's some advantages I think that we'll be able to highlight in this tutorial. Okay, how's this going? Yeah, that's a good idea. Yeah.
Question. Once we get this, we use our Anaconda Jupyter notebook.
Yeah, that's a great question, and I should have put this up there. So if you just open up a Jupyter notebook like you normally do, this package.add iJulia, this magic incantation is going to add a Julia kernel to your Jupyter notebook.
Does it matter if we have multiple Anaconda installations? Does it find multiple?
I don't know. I usually only have one Anaconda installation at a time, but it'll do at least one of them. Are there any other questions? So I'm going to going ahead and slide. So if you want to get a picture of this, or you could even just go straight here and you could find this slide in the notebook. I saw a hand up.
Yeah, I'm just wondering if you could run that package.add in your notebook, or do we have to do it separately?
Yeah, so you won't be able to open the notebook until you run it. So you have to open up Julia and run that, and then you'll be able to open a Jupyter notebook and you'll have an additional kernel. Okay, so CC7768 PyData DC Julia. That's where all of this information will be. So I told you who I was. I guess one disclaimer, I'm not on the Julia development team, so nothing I say is set in stone. This is kind of possibly incoherent ramblings of someone who is fond of Julia and thinks highly of the Julia group. So what's Julia? So has everyone heard of Julia already? So it's this new-ish programming language. I think with every year we can't say new anymore, but it's relatively new. And it's designed to be both high level and high performant. And what do I mean by these things? So when I say high level, I mean it's going to look a lot like some mix of Python and MATLAB. So the syntax, I think, will look really familiar. It's going to have dynamic types. It's going to help you for kind of you'll be able to rapidly prototype code in Julia, just like you would with Python or MATLAB. But there's this additional thing. So kind of writing vanilla Python or vanilla MATLAB, you'll run into these problems where you get to an inner loop of some function and you have to go out and you have to write it in C to get the speed that you need. Hypothetically, you don't need to do that with Julia. And so I put this potentially because if you write bad Julia code, then Julia won't be able to do a good job kind of writing code itself, and the compiled code won't be very fast. So it's based on the same technology. Have a lot of people here used Numba? Yeah. So it's based on the same LLVM technology. So it's really good. One thing I like about Julia is it helps solve the two-language problem. So you look at kind of the core Python developers, like these guys writing pandas and NumPy. A lot of what they do ends up being in C or C++. So a lot of Julia is written in Julia. So modulo like linear algebra and things and standard packages like that, it's written all in Julia. So one red thing, so sometimes naively written code can suffer performance penalties. This is true in all languages, but if you're like really bad, if you write really bad Julia code, it can be slower than other things you would run into. So this is kind of a warning for the future. So the three guys in charge of Julia, the co-founders are Jeff Bezanson, Stefan Karpinski, and Viral B. Shah. They're all great, and I think everyone should have downloaded the 0.5 release. If you have another one, most of this code will still probably run. Okay, so kind of the natural first thing to do anytime you start a programming language is run hello world. So, so does everyone have a notebook, or should I wait like 2 more minutes for people to get things installed and set up?
The downloads take like 5 minutes.
Oh. So I see. So the download speed is a problem. Okay, well, I ran hello world on behalf of everyone here. So hello Julia world. You'll notice in Julia we're using a println function. So that's for print line. They have a print function, but it does kind of the same thing it would do in C, where it just prints things one after another without a line break. See, this is the Spencer, the one I told you got me into Julia. He's kind of rapidly helping me finish up some plots that I wanted to show you guys. So, so thanks, Spencer. So great. So I think the best way to learn a new language is to do a simple example. So the example that's natural to me, maybe other people have other ones, is just a bisection function. So if you think back to, I don't know, did we do this in high school? But you have some kind of a smooth function, and it crosses 0. So on one side of this 0, it's negative, and on the other side, it's positive. And this algorithm goes like this. Find a point exactly in between these two, so find their midpoint, and check whether it's positive or negative. And depending on whether it's positive or negative, update one of the endpoints, and this interval gets smaller and smaller until you're close enough to 0. So what do we have here? So we have, first, to declare a function, you use the word function. So this would be the equivalent of a Python def. Then you put the function name, and then you have the function arguments. So everything to the left of the semicolon is kind of standard argument, and everything to the right would be a keyword. So if you wanted to enter these arguments, you'd have to type out max, iter, or tall. So you set default values just like you would in Python with just equals a number. And then this is maybe a bit different. So putting this here isn't necessary, but what it does is it tells the Julia compiler that f is a function. And so you actually you don't get a performance gain for this. It's, in my mind, it serves as documentation to yourself about what types you want things to do. And I don't want people passing an f that isn't a function to my bisect function, because that's the function we want to find the 0 of. So it gives you a chance to kind of enforce the types that you want to come into the function. So you have tuple unpacking. This is, if you've done C, you'll recognize this is a ternary operator. So the way to read that is if f times b is greater than 0, which means that f of a and f of b are either both negative or both positive, then raise an error, because to find the 0, we need them to be on different sides of the 0. So the way we raise an error is just error with a message. And then, so it reads, so if that thing is true, then do this first part, raise the error, or else do nothing. So this is just question mark, and colon defines the ternary. Yeah?
Is that cut off? Or is
yeah, that's cut off.
It's just NG.
Yeah, there's an NG at the end. They just disappeared. They're invisible. I like that. So then a for loop. How many people have had the displeasure of writing MATLAB? so kind of a lot of us. So you'll notice. I don't know. I don't totally hate this, but they have end statements. So notice with this for loop. So I don't need the indentation, but kind of Python has given me these good habits of indenting all of my loops and my blocks and making my code readable, but I don't need it. The way it reads that is for I equals 1, and 1 : max iter is just a range variable, like it would be in Python. And then I have to end my for loop with an end statement. So here's another ternary operator. And then here's an if-else statement. Notice it also has an end. And then it raises an error message if it fails to converge.
So
Yeah, go ahead.
the first if statement is all the one line kind of thing.
Exactly.
Question mark. The second one
Is just the normal
if
if.
you do either one interchangeably or
Yeah.
is there a performance difference?
I think they're interchangeable. There's also another they use. I think some people aren't fans of it, but in case you ever come across it, you could do some. Here, let me type it and then I'll talk. So this and is like an and statement, and so Julia evaluates first the left-hand side of code. And so if it evaluates to true, then it goes to check the other side, but we've used that other side to return something instead of to evaluate another conditional. I saw another hand, yeah.
Sorry to bring about that, but the last
Yeah, of course.
arguments to the function.
Uh-huh.
Are you setting up default values there?
Yes, exactly.
And why the semicolon?
So the semicolon it's splitting kind of your normal function arguments that you have to supply every time unless they have a default value, and keyword arguments. So I think, but don't quote me on it, I think all of your keyword arguments have to have a default value. And so if I wanted to call these, I'll do an example of it in a second. If I wanted to call these, it would be max iter equals and tall equals if I wanted to change it. Yeah.
Real quick question. For your function type declaration up there,
Yep.
Can that be anything, or is function an actual recognized variable like Julia?
Function is a type.
Okay.
So you can use these for any type. So we could impose, for example, these are float 64s by doing something like that. So any type that Julia recognizes, you can specify that you'd like that argument to be of that type. Yeah.
Really quick question. Is it a white space question? Is it as picky as Python? And I noticed that with your with your declared if statement, you've got like one space.
That's embarrassing. I know.
Is it fussy?
No, it's not at all.
Oh, okay.
It'll totally ignore the white space, but kind of my moral grounding.
Does that include new lines?
So it does, yeah, so it cares about new lines. You can do the MATLAB-y colon thing. So I think if we did that, it would treat it as the same, but I don't like that. Yeah?
So unlike MATLAB, you don't have to expect it to put a semicolon at the end of each line.
No. Yeah, it'll do the same thing. So when we get to iJulia, if you don't want it to display something, you should put a semicolon after it. Okay, so this is like the syntax overview. So ask questions. I'm going to assume everyone's experts in 5 minutes. Yeah.
Can you explain the last end statement? Is that?
Yeah. So this matches with the function keyword.
And then the what?
So one ends the if statement, one ends the for loop, and one ends the function?
Exactly right. Okay.
So the last error, there's. Oh.
Oh yeah, that's a.
If the abs executes, it'll return, and if it doesn't, then we'll get the error.
Right. So we want it, so this is just a little trick. If it ever returns something inside the for loop, it'll finish. And if not, then we know we went past our maximum iteration. But that brings up another point, this $sign. This is string interpolation. So what this will do is it'll look for the variable max iter, which is 500, and it'll say fail. When it prints, it'll print failed to converge in 500 iterations. Thank you. That was something I wanted to mention, so that's. Okay. How is it coming on the downloads? Slow. Okay, well, that's unfortunate. Okay, so we can do that. So the other thing you can do is you can do shorthand function definitions. So this f of x equals x cubed basically just translates to function x return x cubed end. So this is a normal function. And if you wanted to do an anonymous function, it would look like that. So Julia knows about both of those. I don't think I ran this code. So let me go back and run this so I have things that work. And lo and behold, the bisect with both the normal function, sorry, I'm on a leash, and the anonymous function, they both produce the same result. Yay. Okay, so just like in Python, you can do comprehensions. Julia doesn't have a list type, so this would be an array comprehension instead of a list comprehension. But it looks the same and acts exactly the same.
How do you put the Python?
Oh, yeah, that's nice, huh? So Julia accepts Unicode. So if you've ever typed LaTeX, if you type /pi, so you'll notice Julia actually knows what pi is, and what's the one they use for the golden number? Phi? Nope. I could guess it, but I don't remember. So they have a couple of these mathematical standard symbols programmed in, but you can also define your variables as these things. So you can say row 1 is equal to, if you want to get really obnoxious, I think you can even do like superscripts and subscripts. It can get really elaborate, but
With the x squared, is that going to be text, or that's going to?
It's going to be text.
It's not going to execute x times.
No, well, there's one way to check. Sorry, this is a. Sorry, so I have to put this down for a minute to type. So, x. Yeah, so it recognizes it as a variable, not a.
Or if you put it on the other side, if you say x equals 2.
And then try x squared.
Yeah, well, it's still defined.
Oh, that's right.
That's not going to execute.
Yeah, so it's not going to see it. So it's defining these things as if they were LaTeX variables, basically.
So are the comprehensions faster, just like?
Not necessarily. So we're going to talk about, they have a new, so this is actually kind of a cool thing. So they've been working on what they're calling loop fusion. So in NumPy and I think it's NUMEXPR, they have a way I think that gets around this. But they're fusing loops. So when you NumPy, when you do np.cosine, np.sine of an array, it creates a temporary, which is np.sine, and then evaluates np.cosine of that. And so it creates some temporaries in between. So they're working on a new feature where it will be smart enough to fuse those together. So it'll compute every element of this array as cosine of sine of an element instead of creating the temporary in between. So I don't know a whole lot about that. I'm not a computer scientist, but it sounds cool. Okay. So comprehensions. So here's just some standard broadcasting that you can do. So what are these? We can do element-wise operations just like you would in MATLAB with dot divide and dot times. Matrix multiplication is just times. You can do solve AX equals B like you can in MATLAB with a backslash. And then this broadcast trick is worth noting. So what it did is it took a column vector and then added it to a row vector, and the output was a 2 by 3. So it's a 2 column plus a 3 row, and it put those together. It knows the dot plus should make things work the right way. So that's this one right here. So yeah. So yeah, so you notice it took the 2 and the 3 and just made them into a 2 by 3. So you can do neat broadcasting tricks. You can do that in NumPy too. So it's not revolutionary, but it's good to know when you come across it. Okay, so this is the thing I was just talking about. This is doing the loop fusions. So if you want the actual details, I have a link where they have kind of a long discussion about what's happening and why they're doing it. At first, I actually kind of disliked the syntax. So if you remember, we defined a function f, and we forced x to be a float 64. And then just in this last slide, okay, so somewhere we defined x to be a vector. Here we go. So it's all of the elements from 0 to 2 pi with 50 spaced in between. And so this function shouldn't know how to do this. But they take this same dot notation for the broadcasting. That's why I put that in the last slide. So if you do the function dot and then the argument, it converts your scalar function into a vectorized function. And I think this is what they're taking advantage of to do these loop fusions. So if we had cosine dot sine dot x. So actually that's it. I think we'll run some benchmarks in a second, but oh, I must not have run some code. Oh, it has an int.
You find x and x squared.
Oh, that's right.
Sorry.
No. I was confused. I didn't think it would have any integers. Thank you for that. Okay, so now it works. So we'll look, when I load up the benchmark tools, remind me to benchmark the cosine dot sine dot of x. And we'll see that it ends up allocating a lot less memory. I think if you don't add the dots, it does something like 300,000 allocations for some big x. And if you do it without, it only does as many elements as are in the vector, I think. So it's cool. So you can call C in Fortran pretty easily. So all this is ccall is a function that helps Julia know how to go call C. So we go get the math library, and we want the log function. And the output is going to be a float, and the input is going to be a float, and we want to evaluate it at 1. So that makes calling C easy. So this is why they were able to wrap a lot of these linear algebra packages so nicely. So you'll look at this, Julia. Has anyone written Lisp? So not very many people. So I think it's kind of like a mind-blowing experience because you're writing, you can use these metaprogramming where you're writing code that writes code. And so so these guys actually, I think, skipped a lot of the steps that they otherwise would have had to do because they just said for every function, do the same type of thing. And so they wrote code that wrote code to wrap the Laplacian BLAS. Okay. How's the download? Slowly coming? You're what? Excellent. So Python is an object-oriented. So this isn't going to be revolutionary for a lot of people here, but everything in Julia has a type. And more than that, there's going to be a hierarchy of types, and you can think about that just as like a parent-child relation in terms of classes, or this abstract base classes, where you can't define an instance of it, but it's there as an organization tool. So we're going to have the same type of thing. So this is, I think, a good example. If I can get I'll use the mouse. Okay, so the numbers in Julia are organized like this. So at the top, there's a type, and so what they call them is they call these abstract types. So you can never have an instance of it, but there are other types that are subtypes of that in some sense. And so so what do you have? So you have at the top numbers, and then you have either complex, which are a type that you can actually implement, and real, which is another abstract type. So the end of each of these arrows will be one of the types that you can actually create an instance of, and everything in between is going to be an abstract type. So you go from number to real, and then you can split things up into integer, irrational, or rational. Then notice Booleans are just going to be a number type, so they're going to get all of the same operations from numbers. And we'll talk about why they have signed and unsigned integers, etc. So when you're thinking about Julia types, this is the kind of thing you want to have in your mind. And then at the top, so this would be kind of at the very top, so beyond number, is something they call any. And so any is bad news because it means that the compiler can't get any information about what you're trying to do. So if you try to add two numbers and it knows that a method exists for adding integers, it's going to be able to infer a lot of information from what you're giving it. So here's some types. So 1.0 is going to be a float 64. 1 is int 64. Boolean, note the lowercase t and lowercase f coming from Python. You have strings. You can tell it that you want an int 8 instead of an int 64. And then you can have arrays. So we'll talk about these in a minute, but inside this array, notice it's telling you some extra stuff about it. It says, not only is this an array, but this array has types of float 64 and 1 dimension. And so these are going to be called type parameters. So great. So here's what I think is one of the really exciting things about Julia. So I think this is neat. So they call it multiple dispatch. So in an object-oriented language like Python or Java, everything by nature is single dispatch. And what does that mean? It means when you have a class, you have a bunch of methods that are specialized on the first argument of that function, which is the class itself. So you pass all of the class methods self. In Julia, they're going to take that a step further, and functions are going to specialize on all of the arguments. So to understand, let's see some examples. So I've written my dumb function, MDF for short. So remember I said at the very top of this hierarchy is the type any. So the first thing we'll do is we're going to define a method for this my dumb function that takes 2 of anything. And it's going to work its way back, and this will act as a fallback method. So all this function is going to do is it's going to print the type of A and the type of B and then return nothing. So tells us the type of A and B are int64s in this case, and then the type of A is a function, and the type of B here is a rational. So what if we might want this mydum function to do something a bit different. So now, let's say we want to specialize mydum function so that when it sees a number in the A or B argument, we want it to tell us that A is a number or B is a number, or if both of them are numbers, we're both numbers. So if we run this, so remember, these are the same functions we've run previous. So these are the same calls that we've run previously, but we've now defined some new methods. So what Julia is doing is it sees that both of these are numbers, which is more specific than any. And so it knows to refer to this method where they're both numbers. And when A or B are numbers, it knows to refer to these other two methods. So notice it's specializing on each of the types of the arguments. So even though these both have one function and one number, the order matters. So this is, you can do some really cool things with this. And we'll talk about some examples, but as a preview, so I'm an economist, and what economists do is solve models and pretend it's the real world. And so when you have these models that are simplifications of the real world, you have to simulate them. But you write this boilerplate code. Like, I can't tell you the number of times I've written kind of a boilerplate code for simulating a model. And then it's like really easy. You need to have like a next function to tell you what next period is going to look like, given a bunch of information today. So this is going to allow you, so you can have like an abstract model at the type, and then you can have different instances of this model, and they can all refer to certain functions that are going to be, that you don't need any more information other than it's a model. So this type of thing I think is really useful for me as a model builder. So now we'll talk about type parameters. So great. So I told you we have this extra information, and this is just going to allow the compiler to specialize even more. So how is it going to do that? So now we have mydum function again, and what do we have? So the new thing here are these curly brackets. So we're making our way, you may or may not notice, but we're making our way down this hierarchy. So we had any which is above number, and then we defined some functions that are based on number. And now we're going to define some functions that are based on abstract, float, and integer. And so these functions are going to get more and more specialized. And so what are we going to do? So we're going to say if you pass us, so this t, so you can only use : to tell a type when it can actually be instantiated, when it can be created. And so if you want it to be a subset of a larger type, you use the caret : And so what we say is that there's some type t, which is an instance of abstract float. So it's either float 16, float 32, or float 64. And if we call mydum function with A and B that are vectors with elements of type t, so this is going to force them to be the same. So that's a good yeah. So this is going to force them to be the same. Then it's going to say A and B are vectors with some kind of float. And in particular, let's change this to with the same kind of float. And then we can do the same thing. This is exactly equivalent except with the abstract integer type. So if we define these and then run this, notice it recognizes that both of these start with the same type of float. But what happens if we change, so if I change this to float 32, so all this is going to do is it's going to create a vector of ones that with type float 32 instead of float 64, which is the default. Does anyone have a guess at what the first one's going to tell us now? Yeah?
Some kind of float.
It's going to tell us some kind of float. So notice, this function forces it to be not only some kind of float, but the same kind of float. So this saw float 32 and float 64, and it said, I don't know what to do with vectors that have different types. So it walked its way back all the way to the first method, which was any and any. So this is kind of cool. Yeah, go ahead.
All the way back to the first MDF?
Yeah. Because these aren't even numbers. These are vectors of numbers, and it differentiates between those two things. Yeah.
So what makes this useful? It seems like it would maybe introduce a lot of confusion if you were to.
Yeah. No. So it totally can. So you're not entirely wrong, but it's going to be able to do some useful things. And so I kind of talked vaguely about having these multiple types of models. And then you might have, what if I wanted to write a function called publish paper? And publish paper took a model and a question. And then we need a solve method for each model, because models differ enough that you have to solve them a bit differently. So you could write kind of the general paper function, and then it's going to dispatch when it gets to the solve question function. And that will depend on the model and the question type. Does that make sense? Great. No, so it's a bit, so you can run into libraries, and if you're not careful, it can get really messy really quickly, and you can get things where you have a whole file 500 lines long that defines the same function over and over again. And yeah, so it's and then you spend your time trying to figure out which one you want. So I think probably in response to something like this, they defined, so the @ is an example of the metaprogramming, so it's going to write a piece of code, but so just when you type @which MDF 1s and 3. So what are we saying? We want this @which says which of the methods are you calling when you try and refer to this, and so it says, I'm trying to call the method that takes 2 arrays of integers that you defined in your input 25, which is just right here. So when you have a file, it will tell you a line number and stuff. And you can set it up to where, if you have an editor set in Julia, if you type @edit this, it'll open it up in your text editor and take you straight to that line. And I think that's exactly because it can get really messy when you're dealing with kind of a bunch of methods that do similar things but on different types. Yeah?
If we go back a few functions.
Yeah. How far?
Here, yeah, right here. The 22.
Uh-huh.
What's the difference between this and the 2 new MDFs that we just defined?
Yeah, so this one is, so note this,
Shorthand?
no, so number, remember, is at the, is at the top of this hierarchy. It's,
No. Yeah, I understand that. I mean, what's the difference between this definition of MDF?
oh, these two?
You're assigning something to MDF, yes?
So the difference between these two.
The difference between this way of doing it and the way we just did it to the vectors at the bottom there.
Yeah, so this is, when it says number, it's only going to be a scalar. So we could define another method that took a vector of numbers and have that be a default fallback for anything that was a vector of numbers.
No, what I'm asking is this way of defining MDF, the difference between this way of defining MDF. Is this a shorthand for?
Oh, just the one line.
Yes.
Yeah. That's just shorthand. So that was, I put it up on a slide earlier, but just kind of skipped past it. So if you write f of arguments equals something, this turns it's an actual function, not an anonymous function or anything. Thank you. Yeah.
So when it walks back up based on the input variables, does it walk back up in the order you defined the MDF and its namespace, or does it?
In the order of the tree.
The order of the type?
Right, the type tree. I saw a hand go up and down somewhere over here. No? Yeah, so it walks its way up the type tree. Yeah.
So you can actually put in sign as a type.
Signed?
Yeah.
Yeah.
Yeah. Just anything in that hierarchy is things that you can actually call a type.
Yeah.
Or types that you can actually use in code.
That's right. So anything in this hierarchy can be used as a type for this tree that it's going to search through in the multiple dispatch. Yeah, and so the other thing I guess to note is similar to Numba. The first time you call one of these functions, it compiles its first case of it. So this is, so we had this function MDF any, and we've called it with a couple of different things. If we ask Julia, if we say methods MDF, it's going to tell us all of the methods it's compiled. So notice this could be an infinite number of methods if we call the function each time, but Julia doesn't know about them until they've run for the first time. Yeah?
If you specify your types completely, does it do upfront compilation or is it still just in time?
It still waits just in time, yeah. Yeah, you can ahead of time compile Julia, but for the most part, it's fine to run it just in time.
Can you combine Julia and Python?
Yeah, so you can. So because so there's a package called PyCall, and so from Julia you can actually access every package in Python. So they have some examples. I'll try and do an example when we get towards the end and talk about packages. So this would be, so using PyCall brings in this package PyCall, and then we can import the Python math library. And then we can evaluate math.sine of math.py minus sine of pi4, which is just the Julia. So this is subtracting the Python evaluation and the Julia evaluation.
And you can do vice versa.
And vice versa, yeah. Well, I don't know if you can call Julia from Python yet. I don't think it's, so because you can compile Julia, I'm guessing you could work your way into it, but I don't think a lot of people have done it yet. Okay. So yeah, so this is sometimes useful when you're trying to figure out what you actually want to do. So type parameters, so we can specialize using those. So yeah, so user types, I think kind of the thing that, so the Zen of Python, I always think of things as honkin' good ideas. So kind of building your own types in Julia is a honkin' good idea. So you should like not only do this, but you should do this frequently. They have a couple of gotchas about where you should specialize on abstract types versus concrete types, but they talk about these in the performance tips. So I put a link here, but this isn't going to cause kind of massive performance issues. It's just a heads up. So great. So we could define our own type. We could define a two-dimensional point that has values x and y. So what does this mean? So remember, so now t, just like when we had our functions, is going to be a type parameter. And so all we're enforcing here is we're enforcing that x and y have the same type. And then, so what do? We can define 2 points. Point A is in string space, two-dimensional string space, whatever that looks like. And then point B is in a two-dimensional real numbers. So floats to be exact, I guess. And so notice now, when we look at the type of A and B, it's actually changed that t to be a string or a float. So at this point, Julia knows that one is a point with types string inside, and the other is a point with types float inside. And it knows that these two types are different. So what could we do? We could define an addition function. So when you define functions on top of base functions like addition, you have to do base dot in front of it. And then because plus is a symbol, you have to put a colon. That's just a syntactic whatever. So, but what do we do is we want to define an addition for points that have type parameter number. So we don't want to be able to add any type except points with numbers. That's just God's law. And so what do we have is we have a point 2D, and we say, how do you add the 2 points? You add their x values, you add their y values, and you return a new point. So we can do a plus a, but remember, a was our point that had strings. So it says, I don't know what plus looks like when you do strings, but when we do b plus b, b was just 1.0, 1.0, it produces 2.0, 2.0. So we can do this. So then you think, what are the possible uses of this? Is this worth the trouble? And this is what I was saying. We can think about defining kind of larger types, and then we can define something similar. So what I'm going to do is I'm going to find 2 laws of motion, LOM. One is going to be a quadratic law of motion. So if anyone likes kind of these chaotic processes, this is just going to be a quadratic chaos process. And then we're going to do just an affine law of motion as well. And so what are these going to look like? The first one, the quadratic, will have a parameter lambda that I'm forcing to be a float. And this is defining like a call method. So it says whenever we try and call this type, what we want it to evaluate is m.lambda times x times 1 minus x. And then we do something similar for the affine, where we do alpha plus beta times x. So run that. So now we can define a simulate function, just like I said. And notice we're defining it on the abstract law of motion. And both of these things were subtypes of the abstract law of motion. So quadratic law of motion and affine law of motion are both subtypes of this abstract type abstract law of motion. And so how are we going to simulate it? We just want to get the last value. So for 1 to t, just keep evaluating this thing and storing it in x, and then spit out x at the end. Oh. There. So I accidentally ran it twice, so it was warning me that I've overwritten my own method. But so now notice when we call simulate, we have to simulate functions. If we ask it for methods simulate, it's going to tell us that there's 2 methods, one with the t and one without the t. And the reason it doesn't say m quadratic law of motion and m affine law of motion is because we just have the abstract type there. Okay, so we're going to use these later, and we're going to draw a pretty graph that I was creating in the last 5 minutes before the tutorial. Yeah,
I thought
go
you
ahead.
needed a semicolon to separate the keyword arguments in the function.
You do. So the cap t isn't a keyword argument. It's an argument that has a default value. So when I called it, notice I didn't specify anything here, but if I put 500, it would have simulated this one for longer than the other one. Yeah, so it can have a default value, so that's what this is doing. It says this function that doesn't have cap t just calls out to this function with its default value. Okay, so that's kind of the main ideas behind Julia. You have kind of this type system that allows you to do multiple dispatch, and this multiple dispatch helps the compiler in some ways. So they ship a package system with Julia, and it's just a Git-based system. There's 2 types of packages that you can have. So there's going to be a bunch of package manager commands, and they're all inside of your base Julia already, and they'll be referenced by pkg.command. So you can have registered packages. So these are mature packages that have a sense of approval. So there's some So there's some guys that keep a big file of all of the registered packages, and they keep track of when they update. And so these are packages that people have approved, and then unregistered are kind of things a lot of people have written offhand or are progressing towards becoming registered. You have to install these packages a bit differently. So if you run package.add forward_diff, forward_diff is a package that does derivatives, and it does it a number of different ways, including doing kind of this automatic differentiation, which I think is really cool. And then if you want an unregistered package, you'd use package.clone and then give it an HTTPS Git repository. So if we do this, it'll probably tell me I don't need to add anything for forward_diff, and then it's going to add this very incomplete and crappy package I've put together and never finished. So once that finishes, oh gosh, this is probably the internet, huh? So once this finishes, so it added these, it went and cloned this repository and pulled it in. You'll want to run this next line to make sure that you never see that code again. So great. So that's how you add and remove packages. So you add them in a slightly different way using package add and package clone, and then you remove them the same way, just package.rm. And then if you want to update to the most recent versions of all of your packages, you do this pkg.update, and what it'll go through is it'll get a list of all of the versions of the packages you have, then it'll compare it with the online version of all of the listed packages, and it'll look for differences, and then it'll fast forward the things that need to be moved forward. So using packages, so if we wanted to use this forward_diff package, then we can see everything in its namespace using just this tab completion. So forward_diff dot, and this tells us everything that forward_diff has inside of it. Some of the things are useful. Other things aren't. So this will show you literally everything. Packages can choose to export subsets of this, and that will, when you do using forward_diff, it'll automatically put that in your Julia namespace. Actually, I looked, and I think this package takes a stand that they don't want to export anything that you don't want, and so they don't export anything. So if I wanted to use this to differentiate the function cosine of x times plus 2 times x squared minus 5x, I could use this automatic differentiation it has and compute the derivative of that function at 1. Okay, so plotting packages. So it's still kind of a dogfight or a battlefield out here. So this isn't even complete. There's, I think, like 3 or 4 more that are serious competitors. So luckily, there's a guy, Tom Breloff. So he's put together and said, it's crazy to have this many plotting packages, and he's written what he calls plots, and it gives you access to whichever of the backends you want, conditional on him deciding to support them. So right, that's exactly right. It's have you seen that XKCD comic where there's 14 competing standards? We should create one that unifies all of them. 5 months later, there's 15 competing standards. So no, so I think it's a bit better than that, because his only goal is to be an API, and this API is going to be the same across all of the packages. And he's done like top-notch documentation, hats off to him. Every time I start something, I never get to the documentation, and he's done a really good job with it. So what we're going to do is we're going to use plots, and we're going to create the same plot with 2 different backends. So notice the first one we're going to use is Plotly. Have people seen Plotly? You can use it in Python too. It's a pretty slick JavaScript library. So it's JavaScript, so we can interact with it. Yay. But if instead we wanted to use matplotlib, because we like matplotlib, it's the Python conference. So we could use matplotlib to do something similar. The first plot with most of these takes a long time because it's compiling a bunch of different functions, but there we go. So that should look familiar. Except I think he's changed some of the defaults.
Looks nicer.
Well, it's like not the same, right?
Yeah.
Like the ugly settings are like home.
Yeah.
So now we could come, so remember we had this quadratic law of motion, and we could create a bifurcation graph. Yay. So I chose PyPlot for this one specifically because Plotly passes everything around as a JSON, and there's something like 250,000 points on this. It takes Plotly a little bit to make something like that. We can also, okay, so this one will take a minute. If you have questions, now is a good time to ask. But we're gonna make an animation using matplotlib. Yeah, really, it's like a minute. But the good thing, I guess, is, let me see if it'll let me go back while it's running. So the nice thing is if we wanted to use any of these other backends, so if we didn't want to make this with PyPlot, but we wanted to make it with one of the other backends that wasn't Plotly to not pass around that JSON, then all we would have to do is change which of the backends we're using. I submitted an issue this afternoon for Unicode plots. It was giving me Stack Overflow. Okay, it sounds like it's almost done. What? It does not support bokeh. You could talk them into it and submit a pull request though. So we have a little three-dimensional GIF. So any of the plotting packages that that support both animations and three-dimensional plots would be able to make this plot. And it's nice because you have this, they have this unified API to interact with all of them. So now, let me restart my kernel real quick. So this was my friend Spencer. In the last minute, he said, Plotly can do animations too, and he really wanted me to, to get this in. So I agreed, and it's a nice plot. So it's our same bifurcation graph, but now animated. Do it again. So I guess making the JSONs one at a time and then pushing all the information into the graph was a lot faster than doing it all at once. And so his workaround was its own nice plot. Okay, so performance gotchas. So this was, hopefully this will catch some of the mistakes you might make without otherwise being aware of them. So they have this package, benchmark tools. It does what you would think it would do. It has tools to do benchmarking. So the first thing to be aware of is you want to make sure your functions are type stable. So once you define a variable, you don't want the function thinking it might change types. So what I have here is this first function. Notice total starts as an integer. And then when we're doing plus equal inside this loop, it's trying to turn it into a float. So this is going to prevent Julia from knowing whether it's an integer or a float. And then when we use it as a float, I'm sure everyone can guess kind of the outcome of this. So what we're doing is we're just going to sum up kind of 10 million numbers. And it's going to tell us some information about that. Great, so kind of the average time was about 70 milliseconds. Notice it did no allocations. That's really good. And it didn't take up any memory. So now what happens when we do this next one? So this is doing the exact same thing, but remember there was this type instability up front where it wasn't sure whether total was going to be an integer or a float. And when this finishes, we'll notice, we'll notice some different things. So it's about 3 times as slow, and about 10% of the time it's hanging out in the garbage collector. So it does automatic garbage collection. Notice how many allocations it needed. So everyone remember how many the first example needed? 0. And then this one needed, how many is that, like 30 million? Yeah, so 30 million, and it took up about 457 megabytes. So type stability is a big deal. One way that you can check this is they have these macros that allow you to kind of introspect the types, and it puts a list of variables up front. So notice this was the stable one, and it says total float 64. And then if we come to this next version of it, it says total is any. So it worked its way all the way back to the top, and it just said, I don't know what to do with this. And you can also actually, a lot of times, another indicator is how long the actual I think this code gets turned into LLVM, but this code, you can look at the LLVM if you want. I don't always advise doing so. So this is a relatively short function, but if we come to this next one and look at the LLVM, it gets a lot longer. So that's not kind of 100% always true, but generally if it's producing short LLVM code, it'll be faster. And then it produces short LLVM code when it can infer things about the types. The other is, yeah, go ahead.
Question. So that any
Yeah.
there, is that ever sort of like a commonly delimited list of specific types? Or is it just like one type or any? Like, because I guess
sometimes I don't know a lot about the insides of the compiler.
Uh-huh.
I think you can have it where it narrows it down, but I don't know 100% for sure.
Okay, I only ask because it says any instead of
int or float or something like that, or real, yeah. So the question is, why does it march all the way to the top to any when maybe it could get away with going only to real?
Yeah.
So I don't.
Okay.
So I don't know if there's. I'm sure people can answer that question, but I can't.
Okay. Thank you.
Yeah.
So does that always happen if there's like any sort of instability in like what type it's going to be? Does it automatically default to any, or just like?
So any is where it automatically goes. So this is similar to his question. I don't know whether the compiler can narrow it down to smaller lists of types. So like maybe if you had int 8 and int 16, whether it would be able to do something different than, in this case, it had a float 64 and an int 64, and it went all the way up. So I don't know for sure.
Do that, or just like if there's any uncertainty, it just says like.
Right. So it wants to be as careful as possible. So that's one of the things. So kind of if it has any uncertainty about something, it goes back as far as it needs to feel safe. And so I don't know whether that means it goes all the way to any, or whether sometimes you can get away with stopping in between. Great. So the other thing that you care about in terms of performance is in Julia, memory is stored column-wise instead of row-wise. So this matters a lot because most of us are Python programmers. And so in Python, memory is stored column-wise. So we can do another simple example. So what do we have? We have just a function that sums everything inside of a matrix. And one of them goes down the columns, and one of them goes across the rows. So we'll make this thing 10,000 by 10,000. And then we'll run both of these benchmarks and look at what it does. Great. So this one allocation took 16 bytes, about 90 milliseconds. Spoiler alert, this one's going to take a little longer. So this one took about 350 milliseconds. Still only need one allocation because everything was type stable, so it's not having to do these crazy checking between types or making sure it infers the type every time. But it's slower. So you can actually see. So this one was about a factor of 3. The other was a factor of 3. So if you make both those mistakes at once, you can easily get yourself to a factor of 10. So these, I think, are the simplest performance tips that you might be able to get. And then these were things I had time for. I think I have 5 minutes. So I have 5 minutes for questions. Did people get it installed, I guess? That's good. So yeah, that was a question. If you guys have questions, I'm happy to answer some questions. But I don't have anything else to say except thanks for coming today. Thank you to Julia contributors everywhere that made this talk possible, and the Jupyter team. And then thanks to the PyData organizers and sponsors.